Everybody stand for the opening prayer and let us feel the presence of the Lord. Amen. Good morning, class. Okay, before you take your seat, I want you to pick the pieces of paper under your chair, make your row straight, and have your chairs properly aligned. Thank you. You now take your seat. For your attendance, who is absent today? None? That is great to hear. So welcome class to our lesson in math. To start off, I have a few questions here. So do you have an idea when mathematics started? Are you familiar with the ancient Greeks? And what do you think their contributions in Greek mathematics? To answer that, I will discuss to you it later. So let's proceed to our activities. For that, here are our rules. Be cooperative, be respectful, participate actively, attend classes on time, maintain a positive attitude, and always do your best. And with that, let us start. So are you excited? You should be excited, class, because today we will have a game. So are you familiar with 4 picks 1 word? So take a look at this. On this first activity, you guess the hidden words here by referring to these pictures, okay? Now, this letter here below will serve as your clue in guessing the hidden words. So let us start. Yes, Marianne, the hidden words are beginning. Very good. How about this one? Yes, Iris, the hidden words are Greek. Very well. And the last one? Yes, Miss Mayette, the hidden words are mathematics. Precisely. Because today, class, our lesson will be about the beginning of Greek mathematics. And before we proceed to our lesson, let us have first the objectives so that we will be guided as we go along to our discussion. Identify the important details in the history of Greek mathematics. Appreciate the importance of Greek mathematics through 4 picks 1 word, matching and jumble words, and solve problems involving Greek mathematics. Alright, let's do the next activity. You will match the column A with column B. You must suit the pictures to their respective names and select the best answer. Okay? Next, arrange the jumbled letters to form the word that are related to our topic. Let's see if those answers are correct. Now, class, for the questions, I want you to focus your attention on the screen. Raise your hand if you want to answer the questions. Are those names familiar to you? What particular topic comes to your mind after doing the activity? Yes, Hasmin? Fantastic! Greek mathematics seems to have been a detached intellectual subject for the connoisseur. All history is based on written documents, although documentation concerning Egyptian and Babylonian is often very precise. So, the primary sources that can give us the clear picture of the early development of Greek mathematics are meager. So let us have first the dawn of demonstrative geometry. Thales of Miletus. Geometric propositions. An angle inscribed in a semicircle is a right angle. A circle is bisected by its diameter. The base angles of an isosceles triangles are equal. If 2 straight lines are intersect, the opposite angles are equal. The sides of similar triangles are proportional. 2 triangles are congruent if they have one side and 2 adjacent angles respectively equal. So how did Thales discover mathematics in Egypt? Yes, Carla? Awesome! Thales was the first to go into Egypt and bring back this learning geometry into Greece. He discovered many proportions himself and he disclosed to his successor the underlying principles of many others. In some cases, his method being more general, in others more empirical. In fact, Thales is traditionally designated the father of geometry or the first mathematician. Thales knew already the distance along each side of the base of the Great Pyramid was 756 feet and that his staff was 6 feet long. It was necessary only to measure the shadow of the pyramid and the shadow of the staff. It was 342 feet from the tip of the pyramid to the shadow to the edge of the base, and the shadow of the staff measured 9 feet. Now, Thales had all the required dimensions for 3 items of the proportion would give him the missing 4th item. The height of the Great Pyramid was h equals sh over s equals 378 plus 342 times 6 divided by 9 is equal to 2 over 3 times 720 equals 480 feet. So let's move on. Pythagorean Mathematics. Pythagoras was born between 580 and 569 BC on the ancient island Samos. Pupils concentrated on 4 mathemata or subjects of study. Arithmetica, arithmetic in the sense of number theory as opposed to calculating. Harmonia, music. Geometria, geometry, and astrologia, astronomy. When Pythagoras was close to 60 years old, he married one of his pupils, Theano. She was a remarkably able mathematician who not only inspired him during the latter years of his life, but continued to promulgate his system of thought after his death. The symbol on which the members of the Pythagorean community swore their oaths was the tetractys or holy fourfoldness, which was supposed to stand for the 4 elements: re, water, air, and earth. The tetractys was represented geometrically by an equilateral triangle made up of 10 dots, and arithmetically by the number 1 plus 2 plus 3 plus 4 equals 10. To Pythagoras and his followers, mathematics was largely a means to an end in which the human spirit was enabled through a mystical contemplation of the good and the beautiful. Music, the best instance of principle. It was concluded that the most beautiful musical harmonies corresponded to the simplest ratios of whole numbers, namely the ratios 2:1, 3:2, and 4:3. Nicomache's Introduction Arithmeticae, the most complete exposition that has come down to us of the arithmetic of Pythagoras and his immediate successors, is contained in the Introduction Arithmeticae of Nicomachus of Gerasa, circa 100. The numbers 1, 3, 6, 10 are examples of triangular numbers. Because of each of these counts the number dots that can be arranged evenly in an equilateral triangle. Similarly, the numbers 1, 4, 9, 16 are said to be square numbers because as dots, they can be depicted as squares. For instance, the sum of 2 consecutive triangular numbers always equal the square numbers, whose side is the same as the side of the larger of the 2 triangles. This can be confirmed geometrically by separating the dots with a slash and then counting them as in the accompanying figure. So the Pythagoreans may have proved these results by first considering the n equations. 1 squared equals 1, 2 squared minus 1 squared equals 3, 3 squared minus 2 squared equals 5, 4 squared minus 3 squared equals 7, n squared minus n minus 1 squared equals 2n minus 1. The theory of figurative numbers. In 1665, the mathematician philosopher Pascal wrote his treatise on figurative numbers. 16 equals 6 plus 10, 25 equals 1 plus 3 plus 21, 150 equals 6 plus 66 plus 78. We begin by placing square arrays containing 1 squared, 2 squared, 3 squared and 4 squared dots adjacent to each other. Next, let us add horizontal rows consisting of 1, 3, 6, and 10 dots, respectively, to form a rectangle of width 1 plus 2 plus 3 plus 4 and height 4 plus 1. This is pictured here geometrically. Counting the dots in the squares and rows should make it clear that 1 squared plus 2 squared plus 3 squared plus 4 squared plus 1 plus 3 plus 6 plus 10 equals 1 plus 2 plus 3 plus 4, 4 plus 1, and consequently that this will be equal to 30. Proceeding along similar lines, one can get a formula for n squared. All in all, we have shown that the sum of the first n squares has the simple expression in terms of n, namely 1 squared plus 2 squared plus 3 squared and so on is equal to n times n plus 1 times 2n plus 1 over 6. A strikingly original proof of the last result propounded by the 13th century mathematician Fibonacci comes from the identity k times k plus 1 times 2k plus 1 equals k minus 1 times k times 2k minus 1 plus 6k squared. So let's move to Zeno's paradox. Zeno was originally a Pythagorean and, like Pythagoras, played an active part in the politics of his native city. The paradox most often quoted concerns Achilles and the tortoise. Achilles, the swiftest runner in Greece, can never catch a tortoise that has been given a head start. For the time Achilles reaches the tortoise's starting point, the animal will have moved to another point. By the time Achilles reaches the point, the tortoise will have advanced somewhat farther. Suppose that Achilles ran 10 times as fast as the determined tortoise and gives at an initial start of 100 yards. Say Achilles ran 10 yards per second. Consider the distance he has to cover. They are successively 100 yards, 10 yards, 1 yard, 1 over 10 yards, and so on. The total number of yards Achilles must travel in order to catch his slower competitor is 100 plus 10 plus 1 plus 1 over 10 plus 1 over 100. Let's move on to the Pythagorean problem. Pythagoras had discovered the theorem. Now, the area of the same square can be represented in two ways, as the sum of the areas of two squares and two rectangles. A plus b squared equals a squared plus b squared plus 2ab. And as the sum of the areas of a square and four triangles, a plus b squared equals c squared plus 4 times ab over 2. A diagram in the arithmetic classic represents the oldest known proof of the Pythagorean theorem. The proof inspired by the figure was much admired for its simple elegance, and it later found its way into the Biganita root calculations of the Hindu mathematician Bhaskara, born in 1114. The early solutions of the Pythagorean equation. A triple x, y, z of positive integers satisfying this equation is said to be a Pythagorean triple. Ancient tradition attributes to Pythagoras himself a partial solution of the problem, expressed by the numbers x equals 2n plus 1, y equals 2n squared plus 2n, z equals 2n squared plus 2n plus 1. The crisis of incommensurable quantities. The most important achievement of the Pythagorean school in its influence of the evolution of the number concept was the discovery of the irrational. The oldest known proof dealing with the incommensurable line segments corresponds in its essential to the modern proof of square root of 2 is irrational. The ratio of these segments is AC over AB equals M over N. To make matters simpler, let us suppose that any common factors of M and N have been cancelled. Now, AC squared over AB squared equals M squared over n squared. Applying the Pythagorean theorem to the triangle ABC, 1 gets AC squared equals 2AB squared, so that the displayed equation becomes 2 equals m squared over n squared. Payon side and diagonal numbers. Payon of Smyrna, circa 130, devised a procedure for reaching closer and closer approximations of square root of 2 by rational numbers. The computations involve two sequences of numbers, the side numbers and the diagonal numbers. We begin with two numbers, one called the first side and denoted by x sub 1, and the other the first diagonal and indicated by y sub 1. The second side and diagonal x sub 2 and y sub 2 are formed from the first, the third side, and diagonal x sub 3 and y sub 3 from the second, and so on. According to the scheme, if we take x sub 1 equals y sub 1 equals 1 as the initial values, then it will become to this. Let's move to Eudoxus of Cnidos. The Greeks used the term logos, meaning word or speech, for the ratio of two integers. Hence, when incommensurable lengths were described as a logos, the term carried a double meaning, not a ratio and not to be spoken. It fell to Eudoxus of Cnidos to resolve the crisis in the foundations of mathematics. His great contribution was a revised theory of proportion applicable to incommensurable as well as commensurable quantities. It was a formidable task and engaged the best efforts of the most notable mathematicians of the 4th century BC: Theodorus, Theaetetus, Archytas, and Eudoxus. Theodorus of Cyrene, born 470 BC, the mathematics tutor of the great philosopher Plato. Perhaps the most brilliant Greek mathematician before Archimedes was Eudoxus. Then the three construction problems of antiquity. The mathematician who dominated the second half of the 5th century BC was Hippocrates of Chios, who is to be distinguished from his more celebrated contemporary Hippocrates of Kos, the father of Greek medicine. Hippias of Elis, circa 425 BC, a near contemporary of Hippocrates, invented a new curve called the quadratrix for the express purpose of squaring the circle. The last one is the trisection of an angle. In the special case of the right angle POQ, the construction is found as follows. With O as a center, draw a circle of any radius intersecting the side of the angle in points A and B. Now, draw a circle with center at B and passing through O. The two circles will intersect in 2 points, one of which will be point C in the interior of angle POQ. Okay class, all of those everything you've done and observed are the beginning of Greek mathematics. So now, let's help some brave souls summarize these concepts yet again. Yes, very good definitions. So class, before we proceed to your evaluation, I would like you to read this. Let's have you reflect on that next meeting in essay form and be creative. But for now, let's proceed to your evaluation. So this is multiple choice. I want you to select the best answer for each of the following questions. Do this for the remaining time and thank you for your active participation today. Goodbye class!